Our second speaker of the session is Serge Fehr on the composition of two-prover commitments and multi-round relativistic commitments.
Yes, thank you. I have to start with pointing out that this talk is going to be mainly classical. I hope you're still going to appreciate it because of the topic, which actually is related to the non-locality of quantum mechanics. Also, some of our results do hold in the quantum setting, but if the interesting questions are still open in the quantum setting. And yeah, so throughout this talk, I'm going to use this fancy classical C and this even fancier Q to distinguish or to point out which of the results or concepts are restricted to the classical and which also hold in the quantum setting. So the topic of this talk is a commitment scheme. Now, commitment scheme is a very important cryptographic primitive. You should think of it as a digital analog of putting a message into a vault, putting the vault on the table, and then opening later to reveal the message inside, so that the following two security properties hold. The binding property should ensure that the prover, so the party who puts the message into the vault, cannot change his mind anymore and cannot change the message that's inside the vault. And the hiding property ensures that the verifier, so the other party, the other person at the table, cannot see what's inside the vault, cannot see the message until to the point where the prover opens it. So as I say, a commitment scheme is a very important cryptographic primitive that has many applications. Now, unfortunately, it's known and also hard to see that it's not possible to have a commitment scheme that satisfies these two security properties unconditionally. Just even true, this even holds if you go to the quantum setting and allow quantum communication or quantum computation. So this means you have to put some restriction on at least one of the two parties. The most common thing to do is to restrict the computational power of one of the two parties. Another possibility would be to limit classical or the quantum memory, or what I'm going to consider here is the so-called two-prover setting, where I assume that the party that produces the commitment actually consists of two parties, and the assumption is that these two parties, these two provers, cannot communicate with each other. So that's sort of quite similar to the setting that Joseph considered in the talk before. So I'm going to show you sort of a simple example scheme of such a two-prover commitment scheme, which is due to a repos, Salval, Simard, and Tab, and is very closely related, as you can see, to the CHSH non-local game. So here we have the two provers, P and Q, and as I say, it's assumed that during the course of the execution of the protocol, they cannot talk to each other. Now we do assume they have agreement on the bit B they want to commit to, so the message they want to put into the vault is just a bit, and we also assume they have shared randomness Y. Now in order to commit to this bit B, the following is going to happen. So the verifier sends a uniformly chosen bit string A to the prover P, and then P sends back either the shared randomness Y or the shared randomness bitwise XORed with the message A. Which one he does depends on the choice, depends on the bit we want to commit to. Okay, so that's the commit phase, and in order to open the commitment, the other prover Q simply announces the shared randomness Y. And the verifier checks the obvious. Now it's almost trivial to see that this scheme is hiding, that it satisfies the hiding property, because the message that the verifier gets is sort of masked with a uniformly random string, so he only gets to see plain randomness. No information on the bit is obviously leaked with this message here. Now the binding property is also not too hard to see, so we have to show that they can open the commitment to at most one bit, to one of the two choices for the bit, and they should not be able to open the commitment to both bits. But that's not too hard to see, because opening the commitment to the bit 0 means that the Q has to send Y equals X, because only then the left-hand side equals the right-hand side if the bit is 0. Similarly, in order to open the commitment to the bit 1, Q has to send y equals x plus a to the verifier, because only then the left-hand side equals right-hand side. So in order to open to both of them, prover Q needs to know x and x plus a. Well, this implies that he knows a, but this contradicts the assumption, because a was sent only to P, and it's assumed that P cannot communicate to Q. Now you may realize that this reasoning only holds in the classical setting. There's some subtle issue that occurs in the quantum setting, but as a matter of fact, the binding property also holds in the quantum setting. By the quantum setting, I mean that the two provers are allowed to be quantum and produce their messages by means of performing local measurements in shared entanglement. The proof is more subtle, and there's some loss in the security parameter. I'm gonna do it that way, otherwise I have to go through all the steps again. Okay, now the title also mentions relativistic commitments. Now, a relativistic commitment, in essence, is just a two-prover commitment scheme, like the one on the previous slide, but where the no communication assumption is enforced by special relativity. So in the example of the CHSH bit commitment scheme, what we do is we remove this explicit assumption that P and Q cannot talk to each other, and instead we time the execution of the protocol in such a way that the event of Q sending this message to V lies outside of the light cone that is induced by the event of the verifier sending his message A to P. And then by special relativity, it's ensured that this message was produced without having any knowledge of the message A. Now this works well, or at least in principle, but sort of one obvious downside is for this to work, the opening phase must take place very shortly after the commit phase, because, well, speed of light is pretty large, as you all know. And this, of course, is not very practical for say, applications. Now, the way to deal with that, or in order to deal with this, people have considered so-called multi-round schemes, where in between they commit at the opening phase there is a so-called sustain phase, during which the verifier keeps on talking to the two provers, and it is timed in such a way that every round of communication lies outside of the light code of the previous round of communication. And we want that the hiding property holds until the end of the sustain phase, and the binding property holds from the start of the sustain phase, so that this sustain phase sort of mimics the time when the vault is on the table, but it's still closed, so prover cannot change his mind, and the verifier cannot see the message. And of course we want that this sustain phase, to keep this sustain phase alive as long as possible, or at least as long as necessary. Now, a couple of years ago, Lungi, Kanievsky et al., they proposed a very elegant such a multi-round scheme. I'm not going to spell it out in detail, because I'm going to explain it at a more high level later in my talk. For now, just want to point out that the actual commit phase is just the commit phase of the CHSH scheme. And furthermore, every round in the sustain phase also looks pretty much like the commit phase of the CHSH scheme, except that fresh randomness is used by the verifier and the provers, and the bit B is then sort of replaced by the shared randomness of the provers that they used in their previous round. Now what's anyway sort of trivial to see, even though maybe you don't have fully digested now how the protocol works, is that the hiding property is satisfied. Because in every round, the message that the verifier gets is masked with a uniformly random bit string. So no information at all is revealed, and the verifier just gets to see pure randomness. Now what's not so easy to see is that this scheme is binding, that it satisfies the binding property. Well, Lungi and al., when they proposed the scheme, they showed a theoretical analysis of this scheme, showing that the multi-round scheme is epsilon binding, so it's binding up to an error term epsilon that is upper bounded by this thing here. Now what you need to realize is that this upper bound is actually pretty bad. It behaves very badly in the number of rounds. So it's in that sense doubly exponential in the number of rounds, which means in particular to get a reasonable error term, the bits that need to be communicated per round need to be exponential in the number of rounds. So in practical terms, you can only deal with a very small number of rounds. And indeed, they also did a implementation of their scheme, but because of this limit to the number of rounds, they could only deal with a very small number of rounds, 4 or 5, something like that. And as a consequence, you can keep alive their commitment or the implementation of this commitment for 2 milliseconds. Now this is where our new result or results step in, and we do a new analysis of the same scheme, of the very same scheme, where we can show that the error is actually bounded by this thing, meaning it grows only linearly in the number of rounds, which actually is also what you actually would expect if you think about it. Now we did not do any practical implementation, but if we take their raw data from their implementation, combine it with our improved analysis, we get that at least in principle we could keep a commitment alive for, well, 10 to the 50 years, which I guess is good enough for all practical purposes, or demonstrates very well the difference between doubly exponential and linear. In addition, or sort of as a side result, we actually get security with respect to a stronger notion of security. So we not only improve the security parameter, but also sort of use a stronger notion of security. So actually, as you're going to see, our result is somewhat general. We show a general composition theorem, which is based itself on new definitions for the binding property, and improved analysis follows more or less as a corollary. Also want to point out that in independent work, Xiaoyu et al. Obtained the same improved analysis of the Lunge et al. Scheme, but their analysis is very much tailored to the scheme, whereas ours is more general, and also their result is only for the weaker notion of security. Okay, so next I want to give you first some intuition for why we actually expect this scheme to be secure, and our approach for proving it secure is to make this intuition rigorous. Okay, let's have another look at how the scheme works. And as I've already pointed out, the actual commit phase is just this commitment, a standard commitment to the bit B using the CHSH commitment scheme. Now then the first round in the sustain phase is, well, syntactically, it's just a commitment for the opening information for the commitment produced in the commit phase. Now I'm saying here syntactically because, I mean, the B is replaced by, the bit B is replaced by a string. The opening information here is a bit string, and actually we don't know how CHSH bit commitment scheme behaves if you plug in a string. And then, so on, the next round in the sustain phase is again syntactically just a commitment to the opening information of this commitment, and so on and so forth. So this means that schematically, the following is what happens in the Lunge et al. Scheme. The provers, they put the message they want to commit to into a vault. But then, instead of just revealing the code that opens the vault, because now that's the purpose, we want to delay the time when the verifier is supposed to get to see the message, instead of just revealing the code that opens this vault, they put this code into a new vault. And then, again, instead of revealing the code that opens that vault, they put that code again into a vault, and so on and so forth, until sufficient time has passed that they're ready to reveal the original message, in which case they just reveal the code that opens the last safe, and then the verifier can open all the safes from last to first one, and eventually obtain the message. And now the question to ask and to answer is whether this composition of commitment schemes is still binding. The subtle issue is that in this relativistic setting, at the time of the opening phase, sufficient time has passed for the provers to be able to cheat the original commitment scheme. Sufficient time has passed for information regarding this commitment scheme to flow from, say, P to Q. So at this point in time, they would actually be able to come up with a code that opens this vault to a different message. But well, the intuition is that this doesn't help them because they had to commit to this code that opens this vault in this manner. Now, well, what we show is that this intuition is indeed true and that this composition of commitment indeed stays secure with a linear blow-up in the error term. Now, sounds easy enough. There are a couple of hurdles that we had to deal with. First one is that the standard definition that is usually used for the binding property in the context of relativistic commitments turns out to be unfriendly for proving this kind of composition. So we dealt with it by introducing new, partly equivalent, partly stronger definitions and showing composability with the help by means of these new definitions. And there's a second hurdle, but I'll talk about that when we actually get there. Okay, so as I've just said, much of our results depends on a better understanding of the binding property of such two-prover commitment schemes in terms of new definitions and relations among them. So I'll say a few words about that. So the standard definition that is usually used in this context is the so-called P0 plus P1 definition, which somewhat informally says that for any way to produce a commitment, the probability to open the commitment to 0 plus the probability to open the commitment to 1 should be pretty much upper bounded by 1, or 1 plus something small. Now, as I say, it's commonly used in the context of two-proven relativistic commitments, but actually also in the context of quantum commitments. But it suffers from several shortcomings, which also has to do that it's not as strong a notion as one might hope for. It's also not as strong as a notion as you get or have, that we have something in the more classical setting. So, in order to deal with, well, issues that arise with this definition, we came up with new definitions, and the goal was to get closer to the intuition of what we expect from this binding property. So what we expect from this binding property is that after the committing, there should exist and by the way, previous definition was tailored to bit commitment schemes, and here I'm talking about general string commitment schemes. So what we want is that after the committing, there should exist a string as that, so that no matter what the provers do in the opening phase, the verifier will accept this string having been inside the commitment or rejects except with small probability. Right? I mean, it just captures that once the vault is on the table, there is a fixed message that it's inside this vault, and no matter how I'm trying to open this vault, you're either gonna see this message or maybe you're gonna sort of reject because I just refuse to open the vault. But then if you think about it, it's not obvious how to formalize this intuition, how to put this intuition into a mathematically rigorous security definition, the mathematically rigorous definition. Now we came up with two possible ways, and I'm not going to spell out, they're quite subtle and there's some subtle difference. Just want to point out that first one is meaningful also in the quantum setting. It's meaningful also if the provers are allowed to be quantum, produce their messages performing local measurements and shared entanglement. The second one only makes sense, it's only meaningful in the classical setting because it's sort of in terms of the classical randomness of the provers. On the other hand, the second one is stronger and the first one is weaker, which I mean, it's quite easy to see if you sort of take some time to digest these definitions. Okay, so in terms of connecting them to the previous, to sort of the standard, more standard P0 plus P1 definition, what we prove is that for the case of bit commitment schemes. In case of bit commitment schemes, the standard notion is equivalent to the weaker version of the two that we introduced. Now this comes in handy because the CHSH bit commitment scheme is known to be secure according to this P0 plus P1 definition, so we automatically know it satisfies our weaker notion of security as a bit commitment scheme. Now for the stronger notion, well, we have to prove it from scratch that it also satisfies our stronger notion of the binding property. But recall that we actually use and therefore also need the security of CHSH as a string commitment scheme. So that's something we still need to look into. Okay, I just want to more or less claim the composition theorem in a slightly more formal way than so far, but without any proofs. Actually, the proof is not so hard. It's a bit tedious, but not so hard once you have these useful or convenient notions for the binding property. So slightly more formal, the statement is the following. We take two prover commitment schemes with some mild restrictions on their shape, and we're going to consider a new scheme, which we then call the composed one, which works as follows. The commit phase of the composed scheme is just the commit phase of the first scheme. But then in order to open the commitment, instead of just revealing the opening information to the verifier, we now use the second commitment to commit to this opening information, and then we open the commitment to then reveal the opening information so that then in the end the verifier can check the opening information for the original commitment. It may look a little bit complicated, but it's nothing else than what I explained before, that instead of revealing the code that opens the vault, you put the code into a new vault and then you open that vault. And what we show is that this composed scheme is still secure if the underlying two components are where the error terms simply add up. And I want to point out this holds for both notions of the binding property, for the weaker and the stronger. If the two components are weak, we secure Euclid binding, and so is the composition, and correspondingly for the stronger notion. Yes. So seems that we're almost done. So now we want to apply this composition result inductively to conclude that this composition of commitments is still secure. So the only thing that we have to show is that the CHSH scheme is secure as a string commitment scheme, because we're sort of plugging in a string here, we're sort of committing on a string here rather than on a bit. Now, bummer, it turns out that it is not binding according to our notions of security. But of course, I wouldn't have gone through all the exercise to tell you what we've done so far if you weren't able to solve this here. Now, the way to deal with it is that we introduced more notions for the binding property, or we call, in other words, we consider some relaxed notion for the binding property. So for both notions of binding property that we have, we consider sort of relaxed versions, which we call fairly binding, where sort of intuitively it gives the provers a little bit more power in the sense that they're allowed to open the commitment to the string that's inside, or to a random string that is outside of their control. I mean, they can cheat and open to a different message than they're supposed to, but then they have no control over the message that the verifier will sort of see inside the vault. And then we can prove that CHSH satisfies this relaxed notion of the binding property. We can extend the proof or the composition result to this relaxed notion. And then we are in business and can indeed apply inductively the composition result to the Lunge-Dal scheme and to conclude that it is fairly binding as a string commitment scheme, that as a string commitment scheme it satisfies this relaxed notion for the binding property. And then the last thing to observe, which is quite easy to see, is that if you restrict the input to a bit, then the fairly binding notion actually coincides with the standard binding notion. So that in the end we do get security of the Lunge-Dal multi-round scheme with a linear blow-up in the error term. And again, I want to point out, I mean, this holds for both the weaker and the stronger notions of the binding property. And the reason why I sort of carry along that the weaker notion, of course, the stronger notion is a stronger result, why I still kept carrying along this weaker notion of pointing out that sort of the result also for the weaker notions, that the weaker notion is meaningful also in the quantum setting, so we're, with the weaker notion, we're sort of closer to being able to prove security of the scheme against quantum provers. But we haven't proven it because the composition result also for the weaker notion is meaningful for the weaker notion, but our proof doesn't apply in this case in the quantum setting. So, which means, well, the obvious open problem, therefore, is to prove security of the Lunge et al. Scheme against quantum attacks, against provers that can produce their messages performing local measurements on a quantum state. Now we have some steps towards that goal. So I say, I mean, we understand the security of CHSH pretty well against quantum attacks with respect to the weaker notion of security, but the composition result doesn't apply in the quantum setting. And on the other hand, we actually have sort of a different version of the composition result that works in the quantum setting, that applies if the provers are quantum, but it requires kind of a quantum version of the stronger notion of security that I had up here, and there we don't know how to prove that CHSH satisfies the stronger version, so which way we try, there's still some loose ends, so there's still some problems to be solved here. With this, I'd like to thank you for your attention.
Okay, we have time for some questions. Yeah.
Can you give us a feeling, why is the commitment time not infinite in this scheme? So what limits the commitment time?
I mean, the intuition is that, I mean, the scheme consists of composing commitment schemes, n times, or n is the number of rounds. And the building blocks of the single commitment scheme is not perfectly secure. So there's sort of a small cheating probability in each block. And so if you execute the block n times, you have n times sort of a chance to cheat, which means that you get sort of a cheating probability n times the original cheating probability. That's sort of the intuition.
Okay, are there further questions? Our next speaker. Just, okay, I don't have any questions. Let's thank Serge. I'll introduce our next speaker. Okay, Yao Yan Shi.
Maybe we can set up his computer.
I'm afraid to do it myself.
Can I ask a question? So is there an experimental implementation of this?
Yes, but I've not been involved in that.
Good answer.
But no, I mean that's I mean this Lunge et al. They set up this scheme where they placed I mean maybe Jed, you correct me if I'm wrong, where they placed the two provers P and Q at two cities in Switzerland. I think Geneva and somewhere else. But I mean Switzerland is not very big, so they can't be that far away. So recently there was a new paper of 24-hour primitive. Okay, currently, recent paper, they have a 24 hours commitment. Yeah.
You ready? Okay, let's thank Serge again.